So I'm back in Winnipeg and therefore I'm back on video. I'll film a short video today so that you have some material to start looking at. So we're continuing on these environmentally transmitted pathogens, and what I want to cover today is a little bit about parameter fitting and a little bit of an issue that arises when we do parameter fitting. And this will serve as a prelude to things we will see a bit later in the week. I'll remind you that last week what I was looking at were a few of those models for environmentally transmitted pathogens, and I pointed out that one of the issues we were having when we looked at how to simulate those was that we were getting solutions that probably didn't make a lot of sense from a numerical point of view. And so one way to address this, of course, is to fit models. But fitting models is not very easy. So let me start with a little bit of an explanation of what it is we do, and then I'll go through a simple example of the logistic function. So not an epidemic model, epidemiological model in any sense, but one model where things are going to work quite well, just to show how things work. And then I'll mention this problem that I was talking about before, which is identifiability. So to begin with, let's talk about what it is that we do when we fit a model. And I should point out that there are varieties of names that you will see for this procedure. So coming from a sort of statistical approach point of view to the problem, you'll probably talk about fitting a model. So some of the concepts you will see today are also coming from what's called automatic control. And in automatic control, we typically talk about identifying parameters, where this problem of identifiability comes in. And I'll start by pointing out that this is what I'm showing you today is a very simplified version of what would be done in practice. And there's two papers that I want to mention, for example, here that are about some more elaborate techniques. So one is by Roda, and it's about using Bayesian inference for dynamical systems. And the other one is by Porté, and it's about model selection, which is a way to select the best possible model out of a bunch of models. So these are more elaborate techniques that we won't cover here, but that might be worth your attention. So the parameter fitting problem is quite simple. The idea is that you're given a set of data points. And I say this and I realize that I have to do something with my slides. I will be back in a second with better fitted slides. Okay, so let's position the problem to begin with. So we are given a set of data points that I'm going to write TI, YI, where the YIs are the different components. The data points are vectors. They can have several measures inside of them. And the TIs are the corresponding time points at which these data points are collected. And we're going to denote I, the interval of time over that comprises all the data points that we're considering. What's important is that we are going to have model parameters. They're going to belong to some set that we're going to denote curly P. And to emphasize that model parameters depend on these, the model solutions depend on these parameters, we're going to write x of t and p, the solution at time t of the model given a parameter point, well, point in parameter space, so a given set of parameter values for the model. Okay, and then the problem is the following: we want to find a value of the parameters, so a point in parameter space, such that the solution that we get for our model most closely matches, let's say, and I'll define that in a second, most closely matches the data points. So how do we do that? I have to here. Now, before we get into the detail, let me point out that we could have a whole different set of models. I'm going to illustrate the methods using an ODE, like an ordinary differential equation. But you could definitely have any type of model that you can think of. Okay? So we could have a discrete time model, we could have a continuous time Markov chain, we could have all sorts of models. The idea overall is that we have a time series of data points. Okay, so we have measurements of the state of a system over time, and we're able to produce a corresponding time series for from the model. Okay, so that we're able to compare the data points with whatever model we're trying to fit. So mathematically, this amounts to doing the following. So we, in fact, want to minimize an error function, okay, that I've written here. So this error function is a function of the parameters, okay? So for a given point in parameter space, so a given set of parameter values of my model, I am going to compute this function here, which is going to be the sum of some function of the state of the system at the time points that correspond to my data time points minus the data points. Okay. So there's a few important things here. So first of all, this function h here is what often is called an observation function. So when you're writing your model for whatever system you're looking at, or whatever problem you're looking at, you will have a bunch of state variables. Okay, you might not have data points, data values for all state variables. Okay, so for instance, take a model, an epidemiological model with a latency period. It's probable that you are not able to measure how many people are incubating with the disease at an instant in time. So you would not have access to L of t. If L is the number of latently infected individuals, you are not going to have access to that measure. So that function h, what it does is it selects in x being the solution to your system, it selects in x the variables or combinations of the variables that you are able to observe, and it compares it. It makes it it puts it in a form that allows us to compare it with the data points. Remember, the TIs, YIs are the given data points, what we have measured, what our experimentalist colleague or whoever is giving you the data actually has measured. And so this way we match the data points to the output of the system. Then we take the difference between the output of the system at those prescribed time intervals for which we have measures, for which we have data points, okay, the observable ones, and we take some norm of this difference. So typically, and most of the time, at least in introductory work, you will be using what's called the Euclidean norm. Okay? But you could want to use another norm for some reason. Okay. And we're not going to get into that, but if you want to go further in the problem of identifying parameters, then it might be relevant to use a different norm than the Euclidean norm. If you have a parameter p, then what you do, okay, you take a given value of a parameter, a given value of the parameters of your model, so a given point in parameter space, then what you're going to do is you're going to compute a solution to the ordinary differential equation, or system of ordinary differential equation that makes up your model. And from that solution, you're going to deduce a value of the error. Okay. And then what you are going to do is then use a minimization algorithm to find a value of E of P, of the error, as a function of the parameters that is minimum. Okay, so that's the formulation of the problem in itself. So let me point out some things. So first of all, what are the yi's and the h of x? Okay. So if you think about infectious disease models, most of the time what you are going to have in terms of data is going to be incidence. So the number of new cases per unit time. You will typically not have access to prevalence, which is the number of cases that are currently in the population. So if you're thinking about an SIR model, for instance, you don't have access to I of t. You have access to beta Si, because beta Si at a given instant in time is the rate at which new cases are generated. Okay, so beta Si is the incidence. So if I'm using the Euclidean norm, my error function for an SIR model, for example, with mass action incidence, could be something like this. I would have the sum for all data points, okay, the yi's and the ti's. I would take the sum of the beta s of ti, I of ti, where this s and I are obtained by solving the ordinary differential equation of the model, minus the corresponding number of new cases, okay, squared, because this is the Euclidean norm, okay, so it's the sum of the squares of the differences between the vector entries, and that's what I would try to minimize. Okay, so here S of t and I of t are the solutions, the numerical solutions to the ODE, and I would do that. Okay, we'll come back to that later, but before we do that, I'm going to show you a very simple example that has the benefit of being very easy to understand. Now, let's look at probably one of the simplest population dynamics model that you can think of. This is the logistic equation, also called the Verhulst equation. And it's an equation that describes, I think you all know it, but just in case, that describes the evolution of the number n of t of individuals in the population when they are subject to a growth rate r, essentially. Okay, so I'm not going into details. And when there is a carrying capacity K. Carrying capacity is how much your system, your environment is able to sustain, how many individuals your environment is able to sustain. And R is the growth rate of your population if it is not subject to intraspecific competition. It's actually a bit more complex than this, but we can take this model as a first approximation. Now, I'm going to show you the example with El Salvador because I went through different population country populations. And El Salvador currently seems to be experiencing for the last 20 years a population growth slowdown. And without getting into detail, the solution of the logistic equation typically goes to the value k, okay, at the limit. And so I was looking for a population that would be slowing down in terms of its growth. I'm going to get the value of the population of El Salvador through time from the World Bank, and I'm going to show you very briefly how to do that. And what I'm going to want to do here is then to find the values of the model parameters R and K here that minimize an error uh, where that error is going to be computed using that formula before, and I'm going to use the Euclidean norm, of course, for simplicity. Now, to do that, we need to set up the system. It's rather simple. We have a right-hand side equation. We've seen that a few times now, so I'm not going to detail very much. We write down the n prime equals Rn 1 minus n over k, which is exactly here. Here it's a single equation. It's quite simple. Quick remark, this is here what I'm doing is I'm obtaining the population info for El Salvador. So I write a little function of, just to make things easy. I'm using that library WB stats, which is World Bank stats, and I'm using that library to query the index SP pop total, which is the total population in different countries in the world. I want the most recent 100 values. There's not 100 values to be downloaded, but it does as much as 100. I'm using the return wide equals false thing. This way, the return value is named value. Otherwise, it would be named SP pop total. And just because I might be manipulating different indices, I prefer to have a return value called value. But that's just a little thing. Okay. So then I'm saying get the data for whatever country I give it as an argument to this function. Get the most recent 100 values. Just keep the date, which is going to be the year, okay, and the value of the indicator for that particular date. Then I need to order in terms of date, because the way it comes out in the World Bank data is from the most recent to the oldest, and I want to change that into the other way around. Okay, this is what I do here. Then I make both of those columns, I make sure that they take on numerical values, not chains of characters, and then I return the value. And later on, I'll call this function by using this call. I'll just say population is get population data from, here in this case, El Salvador. Now, when you are fitting using this simple procedure that I was describing earlier, sort of theoretically, the important part where, and I wrote first that this is the function that does most of the work, but then I corrected myself and said that actually this is not the function that does most of the work, but this is the function where you need to do most of the work. So that function that you write, what it does is it takes as input the parameters and maybe other parameters. So you have the parameters that you want to find, the parameters that you're fitting or you're identifying, okay? And there might be other parameters that you're not trying to fit, okay? You might know some values for some of the parameters of the model, but you are interested in fitting some of them. So that error function needs to take as input those parameters you want to fit and any other parameters. And what it does is in this particular case that we're looking at right now, because we have an ODE, it takes the solution of the ODE and it computes that E of P that we saw before. Now, one remark, if you're using the ODE function from DE solve that we have seen in the past, one thing you have to keep in mind is that function ODE or whatever function from the DE solve package, it's very convenient for this kind of task because it allows you to specify at what time points you want your answer to be returned. So, for instance, suppose I have data points that are given at the time t equals 1, 2, 5, and 10. Then when I call the numerical integrator, what's important is that I should remember to say that the times at which I'm calling this, and most importantly, it's because it works in the inner working of the code doesn't work at the times you specify, but the solution will be returned. If I write times equals this vector, the solution of the ODE will be returned at these times, which means that the comparison with the data points is going to be very easy. Okay? Given that return value, you then compute the error. Okay? And that function is the function that you're going to provide to a minimization routine that is going to vary p, the parameters, in order to find a minimal value. So let me show you how this works. So here, it'll take several slides to set this up. I'm making a function. These are the parameters that I'm going to vary. These are other parameters if there are any. These are the data points. And just because you might want to change this sometimes if you have numerical problems, I'm also specifying which ODE method I'm using. Here, this is a fourth order Runge-Kutta method, okay? So if I don't change this argument, by default, I'll be using a fourth order Runge-Kutta method. So here, you see these first two lines. This is where I say that the parameters I get, so this is what the optimization function will make vary. The parameters I get from the optimization function, the one that's called R, I set it to be parameter.r. Remember that in the ODE, here, my parameter is this, and I'm going to use it here. Okay, so the R and the K that you see in this function are the ones that I want to vary. And this is what I do here. Okay. Then I set my initial conditions. What I'm going to say here is that my initial number of individuals is going to be the first value in my data set. My data set is going to be the population of El Salvador. I think it's from 1960 onward. So N here is the original N is the value of the population of El Salvador at that time. And I set the initial condition, compute the solution to the ODE with these parameters. You see the times, and this is what I was saying earlier. The times, I set them as the dates that are in my data set. So in this particular instance, it's going to be the years for which the function I wrote earlier to get the population of the country that I'm interested in returns values. So in practice, it's going to be from 1960 or whatever on to 2021, or I think that's what we have as the last data point. But it is going to be precisely at the same times, same dates as are in my data set. Okay, so here, solution sol contains the solution of the ODE. Now, one little remark, which is very important, I think. Um, so, very often, what you'll end up doing is having to decide that some regions in parameter space should not be explored. By default, you're going to be varying the different parameters that you want to identify, whose value you want to find. You're going to be varying them in some interval. But there can be combinations of these parameters that you don't want to consider. So one good way to exclude some parameters is to do something of this form. I mean, you can adapt it to whatever problem. So what you can see here, what I'm doing is I'm saying if the last time point, okay, so this is the last time point here, if that time point is less than the last time point in my solution, in my original data, then probably what happened is that my parameters were such that my solution exploded. Okay, the population exploded. This is not possible with this particular model that we're considering because a logistic equation cannot grow, the solutions to a logistic equation cannot grow unbounded. Okay, so here this is a test that is not required with this particular model, but if you have a model with birth and death, for example, and you take birth larger than death, it is possible that you'd end up with solutions going to exponentially increasing out of range. And so your numerical integration routine would stop before the end of the run. So if I do that, then if I say return infinity, inf here is infinity. Okay. What this is saying is that I'm computing my error, and if this condition triggers, then my error is infinity. And remember, I'm going to be using a program that wants to minimize things. So if my error is infinity, this is clearly not a good solution for a minimum. So by doing this, I'm making the, the code that I'm using to do my optimization sort of be aware of things I want to avoid. So let me give you an example that I think is more relevant here. I could want, for example, in an epidemic model, to exclude regions where R0 is greater than, say, 10. I don't know, I'm looking at some model. I know that R0 is probably going to be between 0.5 and 5. I'm not interested in solutions which in parameter values that would generate an R0 greater than 10. Well, I could do this. I could create a test and say, well, if the parameter values that you're testing are such that R0 is larger than 10, then just make an infinite error. Okay, so that's a good way of excluding regions in parameter space. I should point out another case where this will come up is one that we're not going to see in this example because I'm going to use a minimization routine that knows where to put parameters, okay, where you can impose where the parameters are. But some other minimization routines, for example, will test any possible values of the parameters. So if you cannot impose bounds, so suppose, for example, your minimization routine wants to give you a negative growth rate. Well, one way to avoid this is precisely to do this. If you have a minimization routine or an optimization routine that does not allow you to set bounds on the parameter values that you're looking for, you can do it explicitly within the error function by saying that if the parameter is negative, then the error is infinite. When the optimization routine tries to optimize and it finds an infinite error, it says, well, this is not a good point. Okay, so this is a way to explicitly constrain the parameters. Now, to compute the error, because I've specified that my ODE output is at the same times as the data points, all I need to do is this. Okay, when I compute the difference between the solution that I've generated with my ODE and my values in the data, I know the time points match. So the two vectors of solution and of data, they're aligned in terms of the times. So by computing the difference, I don't need to think about what times they're generated at, because I know my solution comes at the same date as the data. So this just gives me the difference, okay, yi minus n of ti. Then I just square it, which gives me the square of the yi minus ti. I've written it as yi minus ti, whereas it was n of ti minus yi before, but because I take the square, in this case, it makes no difference. Okay. And then the last instruction that I give is take the sum of the resulting vector, and that gives me the sum of the differences. Okay. So I'm done. I have an error function that, given a set of parameter values, is going to compute the error. And now I'm going to use an optimizer to do the actual work, which is to find optimal values of P such that I have a minimal error. And I'm going to do it here using what's called a genetic algorithm. And I'll explain a little bit more in the next slide, but I'll point out here first what the call would look like. And I'm going to detail this call in a second. It's a library that's called capital G, capital A, GA for genetic algorithm. And the call that I'm illustrating here is this one. Okay, so let me go through this call to explain what's happening. So the first thing that I should say, so a genetic algorithm, if you're not familiar with the idea, it's an algorithm that mimics the evolutionary dynamics of a species towards increased fitness. Okay, so the idea is that I'm considering genes, and my genes are actually points in parameter space. So here, a point is a value of R and a value of K. Okay, so a given value of R and a given value of K it's a two tuple. Okay, it's a pair of values, and that is considered like a gene. And the fitness of that gene is the value of the error function. Okay, the error fit function that I wrote earlier. I take a value of R, a value of P, I compute the solution of the ODE through, given these two values, I compute the sum of the differences between the point, no, I compute the differences between the point, I square these differences, I compute the sum of this is my error, okay? And what the genetic algorithm wants to do, the way it's implemented, is it wants to maximize fitness. Okay, so it's looking for the highest possible fitness. Here, I want to minimize. So you'll notice that I'm calling, if I go back here, you'll see that I'm calling with minus error fit. Okay, I'm doing this because I want to maximize this negative number. I want to be as close to as possible to zero coming from negative values. Okay, this is just a little trick because this is a maximizer, and to minimize when you're using a maximizer, you just flip the sign. Okay, so what happens? This call, if you go back here, you'll see I have at the bottom here, I have population size. So population size is how many genes, so how many different values, different points in parameter space I'm using. Okay, so I'm using 500. And what happens is I can specify some guesses. And you can see here, this is what happens with my suggestions. So here I'm saying, well, my first suggestion, so the order in which I present the genes is important. So, I mean, not the genes, the elements of a gene. So R and K. So here I'm taking as my guess a growth rate of 1 and a carrying capacity. I should point out I've done that before. Carrying capacity is going to be here, this K. Wait, yes, I forgot this slide. So here I'm just saying, okay, I'm taking a random value. This is going to be modified by the function, okay? But I am taking as my guess of the carrying capacity. Remember, carrying capacity is the limiting population. I'm taking it to be the last value, or the biggest value, let's say here, the biggest value in my data. Okay, so where am I here? Uh, I I can specify these values as I did here. So I've taken a random guess. This is simply saying one of my initial 500 genes is a gene that has R equals 1 and K equals the maximum of the population. And then other than that prescribed, and you can specify more if you want, okay? It's you can specify a vector of suggestions. But other than those suggestions, what it does, it takes values at random, typically, between these numbers here. So here this is saying lower is the lowest value that I'm allowing. So I'm saying, well, I'm taking R to be between 0, 1, and 10. And I'm taking K to be between 1 million and 10 million. The current population of El Salvador is about 7 million, if I remember, something like this. Okay, but so this is allowing me to specify that range. If you recall what I was just saying before, there are algorithms that are not going to allow you to specify this. And this is where in the error function, I could implement a check that these values, that the R and the K are indeed in these specified values. And if they are not, I would put that the error in that case is infinite. But here I don't need to do that because I can specify the upper and lower bound for the parameters. Okay. Um, and then what happens? Max iter is one that I have set to 200 here. What it does is it allows a maximum of 200 iterations. So what happens is it computes the fitness of all the genes that are the 500 genes that we've created, and it keeps the genes with the highest fitness. So the largest value of minus our error function here. And then what it's going to do is it takes those and it's going to perform what are sort of analogs of genetic operations. It's going to do things like mutations. Mutations is going to consist in a little variation of one component of a gene. So it's going to change R a bit or K a bit. It's going to do crossovers. So it's things like, okay, if I have two genes that are quite nice, I might want to interchange, for example, the value of R in one with the value of R in the other one. There's a bunch of operations like this that it does, and it does so in order to generate, again, pop size genes, and then repeats the process. Okay. There's a lot of additional things that you can do in order to change the parameters of the search. Okay, but here I'm using relatively simple parameters. Two interesting things that I have in my call earlier, and I'll point out here. The first one is that you can parallelize cheaply, very, very cheaply, uh, the call to a genetic algorithm. So if you think about what's happening, I said what you do is you have this population here, we've chosen 500 genes. We have these 500 genes, and we compute the fitness of each of these genes. As you can guess, there is no link between computing the fitness of this gene and the fitness of this gene. They can be computed independently. Okay. That means if I have two different computers or two different cores on the same computer, I can do the computation in parallel. And so putting this parallel equals true option means that it uses as many cores as you have on your machine to perform the same number of operations simultaneously. So that results in quite an important speed up. The other option that's quite nice here is optim equals true. So this actually is a bit the other way around. So I'm not going to detail here at all the type of algorithms that do optimization. It's an entire field. It's a very vibrant and active field of research. But essentially, that technique that I'm showing you is what's called a stochastic optimization routine. There are also deterministic optimization routines. The best well known is typically what's called gradient descent, where the algorithm tries to descend along a gradient it computes a gradient of your error function, and it tries to follow that gradient downward. Well, what this option optim equals true does is that from time to time, when you have a number of iterations of your genetic algorithm that doesn't change, it stops the genetic algorithm proper, takes the best solution that you have at that point, and tries a little bit of deterministic optimization around that point. Okay. And then it kicks back into a genetic algorithm. And yes, just one remark. If, like me, you have the chance of having a computer with a very large number of cores, remember to say something like parallel equals 124, which says how many cores to use. Or, at least the last time I checked, does not handle more than 124 simultaneous computations, unless you recompile, etc. But the base version of R doesn't like this. So if you have 128 cores like my machine does, then it fails and it returns an error if you don't set the maximum number of threads to be 124. But you might also want to use this if, for example, you have a very tiny machine, you want to do some parallel computation, but if you use all the cores when your machine just is unusable for a while, then you might want to specify a number of cores that's lower than the number of cores that you have. That's it. So I run the program, I get my optimal solution. So here, what's important is, I'll point out, you can see that I've taken my initial condition to always be the first point in my data set. So I've taken n of 0, n of 1960 in this case, the first time point, to be the value of the data at that time point. And this is the best fit that it found. So I'll point out, this is, as I said, a stochastic algorithm. It might be worth running it several times or letting it run for a large number of generations or trying different values, because it is possible that you will find a better fit if you use different values. This is worth keeping in mind. But you can see this, okay, the white dots are the data points and the red is the fit. Now, one thing that might be interesting here, I pointed out that I started out with n of 0, the first time point, be of the data, the value at the first time point to be the one in the population. But I might want to actually let this vary as well. So I could add this line to my error function. Okay, when I'm at the beginning of my error function, you remember I have two lines that were saying vary r and k. Well, I can also say I could vary n0. Okay, because nothing tells me that necessarily that is the value that I must have. Maybe there's a better fit by letting also the initial value be chosen. And in that case, my call needs to be include R, K, and N0. Okay. And if I do that, well, you can see that here it's found a better fit. I'm not showing you the error, but the fit is better here than it was in the previous one. I'm closer to these data points, but that is done at the expense of having an initial value that is actually not equal to the one that I had in 1960. Okay. Okay, and briefly, I want to, I have 3 slides on this, so it's going to be very brief. Um, for perhaps not a lot. I want to talk about the issue of parameter identifiability. So this is something that's going to come up if you're doing this type of procedure. Now, it's very easy to understand what's happening. So remember that our aim is to minimize as a function of p this function, this error function e of p. Now, when you're doing this, you can see this is a complicated function. Okay, so these are the data points, that's fine, but these are solutions to an ordinary differential equation, and I'm taking the norm and I'm taking the sum of this norm, and you can guess that it's very likely that I can find several values of p that are going to minimize my error. And another problem that might arise is also some of the values of p I find, I might not be looking because parameter space is huge. Okay, if I have even 2 parameters like before, and I have 2 positive parameters, I have the entire positive quadrant of the plane to explore. I don't know. Maybe some of the parameters I found are only really locally valid, and maybe if I go a bit further away, they're not like this. And all of this has to do with what we call the identifiability of the parameters. So let me show you a very, very simple example, but that is quite telling. So this is adapted from a paper from Bellman and Astrom in 1970. Okay, so this is a identifiability, just a remark in passing, it's very funny in a sense how science repeats itself all the time, because identifiability was highlighted as a big problem in the 70s and the 80s, and there was a lot of work from the even mid 60s to let's say the mid 90s on identifiability. And then most people forgot about identifiability. And now, with COVID having generated so much work on parameter fitting and so on, all of a sudden people are rediscovering identifiability as being an issue. But I really want to point out there's a lot of literature from the 70s and the 80s about identifiability, and it's really worth taking a look. So in particular, so as I said, there's this example of Bellman and Ostrom that is quite telling. So what you have is a system like the one there. The idea is that you're taking a tracer, some sort of medication. I mean, it's a tracer, but it could be a medication. You take a medication and you inject it to someone. You inject it in their blood system. Oops, this is not X2, it's C2. Okay, so C1 is how much drug there is in the blood system. C2 is how much drug there is in particular in the gastrointestinal system. You're injecting a drug that has to do with the gastrointestinal system in some way, or it's digested, I don't know exactly, but what happens is there's an exchange between the blood and the gastrointestinal system. And after injection of a drug, the injection of a drug takes place at the rate U, okay? Um, and what you observe is the concentration of drug. So you take a blood test from someone, you make an injection, or you inject them continuously, and then you take blood tests, and Y is going to be, so my observation variable, it's how much drug there is in the blood. Now, if you want, if you think about it, what's going to be important is that the injection that the sort sorry, the sampling that I do is going to be I'm going to observe some liquid volume of blood. I'll take, I don't know, 1 cc of blood. Um, but that blood, if I want to know how much drug there is in the system, in a way, I have to know how much blood you have in your body. Because I'm taking 1 cc of blood, but I don't know how much blood you have. So that 1 cc, is it 1 of 5 liters that you have? Or do you have 7 liters or something like this? Okay. And now there's transfer rates between the compartments and out of the compartments. So you can see 0 here, the index is from I to J. So 0 being outside, it goes to other components or it is excreted. So I have U entering, I have K10 and K20 going out from C1 and C2. And between the drug system and the gastrointestinal system, I have exchanges and they take place at the rate K12 and K21. Okay? And U here is the injection rate. So let me even simplify this and say that rather than a continuous injection, let's do a single injection. Oh, I forgot to remove the U here. So there's no U in this particular case. What we do is that we inject originally a mass or volume D of whatever drug. Okay, there's initially no drug in the gastrointestinal system. It's only put in the blood, and then we look at the evolution of this system. So this is a linear system. We're not assuming that there is anything happening to this drug except being exchanged between the blood system and the gastrointestinal system, being excreted, and being originally injected. Okay, so at the initial time, I put D units, let's say, of drug, and then the evolution of the drug in the system is given by this. And what I do is that I take, so it might be at some instance in time, it doesn't really matter here, but I'll be able to make a measure. And that measure that I do is when I take my blood, my blood sample, what I observe is how much mass of C1 there is divided by how much blood there is. Okay, because the concentration of C1 in your body is how much mass there is divided by how much volume of blood there is to for it. Okay. And so what we have is we have 5 parameters to estimate if we want to understand this system. We know how much we inject. This is our initial condition. We know how much we inject, but we have to find out what the exchange rates are, what the excretion rates are. Excretion rates would be like what's the half-life of the medication in your body, etc. Okay, so I need to find these arrows K10, K20, K12 and K21. I want to find their values, but in order for me to be able to know how to correlate those masses together back to what I check, I need also to know how much blood you have in your body. Okay, so I have 5 parameters to find. Now, this is a very simple, if you go back to this system, this is a linear system of differential equations. It can be solved explicitly. Okay, it's a system of 2 differential equations together with an initial condition. This one I can find once I know C1 of t. Okay, so this is just 2 equations, 1 initial condition. So I can solve explicitly using, for example, the matrix exponential. And what I find is that when I plug the solution back into my observation equation, I get an equation like this. Capital K1 e to minus lambda 1t plus capital K2 e to minus lambda 2t, where the capital K's are given by these values, where the lambdas are given by these values. Okay, I'm not going to get into details, but what you can see is that, okay, I have my y of t. Y of t is going to be the observation variable. And I need to find K1, well, I can find those, but what's important here is that I have 4 equations, but I have 5 unknowns. So I'm not going to be able to find a unique form for this. Okay, so what we say is then that the model is structurally unidentifiable. So it is not possible to reconstruct y of t uniquely from these four values here, because there is one more thing that I have a v1, okay, here. So there's 5 unknowns and only 4 equations to describe these 5 unknowns. Okay, and that's a very, very simple example. It's a linear model. Imagine what happens when you make things non-linear. Things become even more complicated. So that's a prevalent problem of which you must be aware whenever you start doing fitting of your models. Okay. And we'll see some problems that arise like this in the remainder of the course that I hopefully will be able to tape tomorrow.